Hello everyone, I welcome you to my presentation entitled A Strategy for Tuning Properties of Edible Coating Compounds During Fruit Waste Valorization. My name is Witness Ndlovu, a PhD candidate at the University of Stellenbosch in Cape Town, South Africa. My supervisors are Professors Chumpangu A and Fawole OA. In this presentation, we are going to discuss the concept of edible coatings. We start by defining them, then discuss the role of pomade valorization in acquiring the components needed for their formulations, then the challenges in tuning the coating properties for a specific target fruit. Then lastly, we'll look at the blending of pomaces as a strategy to enhance the coating properties. Edible coatings are an emerging alternative to traditional food packaging. They offer biodegradable and food-safe options that extend the shelf life of fresh produce. However, the effectiveness of these coatings depends on the careful tuning of their properties. Factors like moisture permeability and mechanical strength need to be balanced to suit different types of fruits. This presentation, therefore, explores how the valorization of fruit waste can provide a sustainable solution for enhancing these coatings. By transforming byproducts like peels and seeds into functional coating components, we can reduce waste and improve the quality of edible coating. This approach supports the circular economy and paves the way for more eco-friendly food preservation methods. By blending the apple, grape, and orange pomaces to leverage on each pomace's unique properties, this study provided a simple, green, and scalable strategy to tune and enhance the properties of edible coating formulations. Coatings provide a natural and biodegradable solution for extending the shelf life of perishable products. The choice of material, which could be polysaccharide, proteins, lipids, or composites, depends specifically on the requirements of the target fruit or food product, which could be moisture retention, oxygen permeability, and or microbial protection. And oftentimes, edible coatings are formulated using a combination of these materials to leverage the strengths of each material. Polysaccharides are good for structure, whereas proteins provide flexibility and lipids provide moisture resistance. Edible coatings preserve the nutrients of the coated fruit. They also regulate the gaseous and moisture exchange between the fruit and its environment. Edible coatings can also avoid microbial attack, and in all this, they maintain the central qualities of the coated fruit and ultimately extend its shelf life. To evaluate the three pomaces for the critical components that are required in the formulation of edible coatings, a metabolomic profiling was undertaken, the results of which are given in the next three slides. The first slide here shows the composition of these critical components in the grape pomace. The pomace had a notably high concentration of organic acids, especially tartaric acid. This acidity is crucial for maintenance of the pH balance and stability of the coating matrix. It also serves to inhibit microbial growth and therefore extend the preservation of the coated fruit. The pomace was also rich in flavonoids, especially catechin and epicatechin. These high levels of these flavonoids provide strong antioxidant properties. Therefore, they reduce the effects of oxidative stress, which can lead to browning and the deterioration of the fruit quality. Also, notable concentrations were procyanidins. These compounds can enhance the integrity of the coating through their binding properties and therefore create a stronger and more resilient film. Pomace was characterized by high levels of sugar alcohols, especially sorbitol. The presence of sorbitol in edible coating formulations is critical as it helps in improving its moisture retention capacities. Sorbitol can also help in maintaining the flexibility of the coating solution over time. The pomace also had a significant amount of flavonoids and organic acid. The flavonoids included quercetin and isoquercetin. These are important components of the edible coating as they are antioxidant agents. Quinic acid, which was also recorded in moderate amounts, is important in the formulation of edible coatings as it can contribute to acidity and stability of the coating solution, thus enhancing the uniformity of the edible film. So the orange pomace stood out with its extremely high hesperidin and naringin concentrations. These flavonoids have significant antioxidant and anti-inflammatory properties. This will help to protect the coated fruit against oxidative damage and improve its overall appearance and texture over time. There are also limonene glucoside and nominate glucoside in notable amounts. Their presence can enhance the antimicrobial properties of the coating solution, making it effective against microbial proliferation. This is crucial for extending the shelf life of the coated food product. The orange pomace also had notable citric acid concentrations. This can help regulate the pH of the coating solution and maintain the stability of the coating over time. That's prevent microbial growth from the coated fruit. To leverage the unique crucial properties of the three pomaces, a blend of the three was made in equal ratios to produce the sample CAJ, seen here on the graph with yellow bars. Its metabolite profile showed distinct concentrations of the flavonoids, organic acids, sugar alcohols, and glucosides. This has potential to offer, firstly, antioxidant synergies by combining the polyphenols from apple, from grape, and from orange. It can also offer enhanced antimicrobial protection by combining the high tartaric acid content from grape along with the antimicrobial properties of hesperidin and naringin from the orange pomace. There is also potential to have improved structural integrity. This is through the presence of sorbitol from apple and the balanced use of organic acids from all the three pomaces, citric, tartaric, and quinic acids. This ensures flexibility and durability of the coating solution, reducing the risk of cracking and ensuring consistent protection. The bioactive compound extraction process followed the green approach where natural deep eutectic solvents were used as extraction solvents at low temperatures of 50 degrees Celsius. Hydrophilic and hydrophobic nades were used in a single biphasic extraction process to produce two extracts. The hydrophilic extract was rich in pectin, antioxidants, and the sugar alcohols, and was therefore incorporated into the edible coating formulation, whilst the hydrophobic extract undergoes recovery of carotenoids and recycling. Additives were further added to the edible coating formulation to improve on its flexibility and applicability. Distinct edible coating formulations were designed for apples and pomegranates. Apples are climacteric fruits which are susceptible to enzymatic browning as a result of polyphenol oxidase or PPO enzyme, moisture loss, and loss of closeness. Its specific formulation included ascorbic acid to arrest the PPO and pomace extracts, which were rich in antioxidants, sugar alcohols, and antimicrobial agents. Glycerol was also added as a surfactant. Pomegranates, on the other hand, are non-climatoric fruits. They are susceptible to moisture loss and microbial proliferation. An edible coating formulation was designed for them, which contained chitosan for enhanced antimicrobial properties in the pomace extract. Sorbitol was also added for enhanced moisture balance and plasticizing effect. The results of the properties evaluated were radical scavenging activity. These were greater than 75%. The viscosities of the edible coating formulations were between 4 to 8 millipascal seconds, and the pHs were between 5 and 6. Other properties are still to be evaluated. In conclusion, blending apple, grape, and orange pomaces before extraction has potential to produce enriched extracts that improve the functional properties of edible coatings. I thank you.